Good morning, everyone, and welcome to the webinar. My name is Caroline Stewart, and I work on the marketing team here at CrateDB. I'm joined today by Tanay Pant, who is your presenter on the webinar, which is Success in the Age of Digital X. Before I hand over to Tanay, I'm going to take you through a few housekeeping items. So if you have problems with the sound or can't see the screen, please let us know through the chat box. We'll take the Q&A at the end of the presentation, but if you do have a question, please feel free to pop it into the questions box, which you'll see on the screen. And finally, we are recording this session and we'll send this out to you within the next few days. So without further ado, I'd like to hand over to Tanay.
Thanks, Caroline. Hey everyone, welcome to my webinar on Success in the Age of Digital X, the grand quadrant of IoT scale databases. And thanks for joining me here. Today we will talk about a couple of topics, which include the Industrial Revolution and Industry 4.0 itself, sensors in factories and why it makes sense to use them, and the kinds of workflows that it enables in an industrial context. We shall then take a look at why digitalization projects fail and what we can do to stop this trend of failing projects. After that, we will take a look at the CrayDB ecosystem and learn about the characteristics of CrayDB that sets it apart from the other databases in this segment. And finally, we will go through a case study of a smart factory, which basically has made six-figure savings in 2018 by making a switch to CrateDB. My name is Tanay Pant, and I currently work as a developer advocate at CrateIO in Berlin. I really enjoy working with time series and sensor data. I'm a tech speaker for Mozilla and volunteer to their various projects in my spare time. I've published books on Firefox OS, building a virtual assistant on Raspberry Pi, and web-based virtual reality. I also run a podcast called Technically True, where we talk about public speaking, developer relations, and data. So if you have some time, do tune in. So let's get started. Dating back to around 1760, the first industrial revolution was the transition to new manufacturing processes using steam and water. It witnessed mechanization, a process that replaced agriculture with industry as the foundations of the economic structure of the society. It was hugely beneficial in terms of manufacturing a larger number of various goods and creating a better standard of living for some. This made machine use much more feasible, and the idea of manufacturing with machines spread more quickly. Machines allowed faster and easier production, and they made all kinds of new technologies and innovations possible. By the beginning of the 20th century, electricity became the primary source of power. It was easier to use than water and steam and enabled businesses to concentrate power sources to individual machines. It was commonly referred to as the technological revolution. So mass production of goods using assembly lines became commonplace. Lastly, just-in-time and lean manufacturing principles further refined the way in which manufacturing companies could improve their quality and output. Around 1970, the third industrial revolution involved the use of electronics and IT to further increase automation in production. Manufacturing and automation advanced considerably thanks to internet access, connectivity, and renewable energy. The invention and manufacture of electronic devices such as transistors and IC chips made it possible to fully automate individual machines to supplement or even replace operators. So this period also spawned the development of software systems such as ERP tools that enabled us to plan, schedule, and track product flows through the factory. Finally, the fourth industrial revolution is the era of smart machines, storage systems, and production facilities that can autonomously exchange information, trigger actions, and control each other without human intervention. It connects the Internet of Things with manufacturing techniques to enable systems to share information, analyze it, and use it to guide intelligent actions. It also incorporates technologies like robotics and artificial intelligence. The development of new technology has been a primary driver of movement to Industry 4.0. The applications for the industrial sector are already enormous, such as predictive maintenance and improved decision-making in real time. Now that we know what the four industrial revolutions were and what Industry 4.0 is, let's take a moment to talk about sensors in factories. Factories all around the world have been working with a number of different solutions to transform the way their manufacturing processes work. These systems aim to control and provide real-time feedback by recording data from different sensors, motors, and valves. All this data that is gathered contain multiple values and parameters, along with a timestamp, which makes this time series data. This complex time series data coming in at high speeds also needs to be queried in real time. This data is sent via protocols like MQTT, via maybe a Kafka pipeline to a time series database like CrayDB, and monitored visually via a dashboard like Grafana, Power BI, or Apache Supersets. So, over the past few years, we have heard a lot about these digitalization buzzwords. So let's now take a look at what's been actually going on with these digital transformation efforts. Well, according to these surveys and reports by institutions and companies, a huge majority of these digitalization and IoT projects fail. And what's worse is that 30% of these fail at the proof of concept stage. Again, companies like McKinsey, IDC, and Microsoft conducted some studies and research around this topic and found out that there are three primary root causes of why this is happening. First of all, we have a lack of necessary skills in the specific industries. Then we have siloed and resistant corporate culture. Well, resistance to change can often be a big deterrent to progress. And finally, we have data and IT infrastructure, which is interesting considering that this is the only technical issue in a list of more people-related challenges. But if you think about it, we have come a long way dealing with data. We have amazing tools and databases out there that have been working quite successfully till now. Then what happened now all of a sudden? If you take a look at the last decade, you can say that it's a machine data world, and machine data means explosive growth. In 2018, we saw a boom in the number of IoT devices and their use cases. In 2018, we saw increase in the use of IoT and sensors in different contexts, such as smart factories and smart cities. The total number of IoT devices is moving towards 20 billion by the year 2020, and every second, another 127 devices are being connected to the internet. Just as an example, take a Boeing 787, which generates about half a terabyte of data during a single flight. And if we talk about the plastic manufacturing industry, there's a wide array of data being produced per bottle. And there's data per production line, with as much as 10 production lines per plant. This data is being generated by around 950 sensor types, and that's just one factory. And this particular company has 180 factories in 45 different countries. That means data on billions of bottles. There's a good chance that the bottles that you use in your refrigerator have been running its data through the Crate platform during their production cycle. But we will talk a bit more about this company and the data generated by it in a while in our case study. So just like we had the 4 ages of industrialization, we also had 3 generations of databases. First of all, we have legacy databases, which are used in an environment with mainframes, with client-server setting, and were used quite often with ERP systems. It dealt with low to medium volumes of data, which was being ingested at low velocity, and the data itself didn't have much variety. So what was expected of these systems was consistency, reliability, and standardization. These databases were made by Oracle, IBM, Terabase, and Sysbase, just to name a few. Then we have the next generation, modern databases, which are used for cloud services, mobiles, and handling big data, essentially web-scale use cases. It deals with high volumes of data coming in at high speeds with a low to medium variety of data. And some of the key characteristics that were required in this case were availability and redundancy, enablement for fast application development, and supporting massive numbers of concurrent users. Vendors like Hadoop, MongoDB, Splunk, Microsoft, and Amazon helped us out with databases for these use cases. Applications and users have forced database innovation in the past. However, the machine data world has outpaced the database industry. There are use cases like connected things, edge computing, convergence of OT and IT, interoperability, and even instances where machines become users. Here, the incoming data volumes are very high, the velocity is very high, and even the variety of data that pours in is very high. There are very specific characteristics that are required from this generation of databases. So we need fast data ingestion and real-time analysis, easy scaling to many locations and machines, and flexibility to operate at the cloud or on the edge. So we feel that there's a serious deficiency of databases in this sector. So this is the spot where Crate lives and the area that we focus on. Before checking out the grand quadrant of IoT scale databases, let me tell you a bit about Crate and what makes it stand apart from the various other databases in this segment. At Crate, we have been working on developing technical architecture in IoT and time series field over the past 5 years with clients like McAfee, Nokia, Rauch, Alpla, and many more. So CrayDB is a distributed SQL database that is best suited for handling industrial time series data due to its ease of use and ability to work with many terabytes of time series data with thousands of sensor data structures. So CrayDB is quite simple to install. You spawn an instance of CrayDB with a single line on your terminal or on Docker. CrayDB uniquely combines standard SQL with NoSQL benefits. It operates on a shared nothing architecture. So various nodes in a cluster coordinate seamlessly with each other, and the execution of write and query operations are automatically distributed across the nodes in the cluster. It is NSI SQL compatible, including joins and Postgres via protocol, which makes integration with tools such as Grafana really easy and prevents lock-in. CrayDB supports distributed SQL with full text search, JSON, time series data, geospatial data, and blob tables. This architecture is quite well suited to containerization, meaning a cluster running on Kubernetes can be scaled up or down as easily as running a kubectl scale command. So scale-up operations can take minutes instead of weeks. And operations like sharding, replication, and rebalancing of data as the cluster size changes are automated. So until recently, workloads like these often required a NoSQL solution like Cassandra, Elasticsearch, or InfluxDB, often in combination with a traditional relational database. So CrayDB makes it possible to handle them in a single system without sacrificing the familiarity and power of SQL. So the fire hose of complex industrial data needs to be handled in real time. And in order to take real-time actions on the factory floor, let's now talk about the next layer of Honeycomb built on the core CrayDB technology, CrayDB Cloud, also known as CrayDB on Azure. So CrayDB Cloud is a scalable cloud service that is hosted on Azure. It is ideal for industrial time series data processing and other IoT and machine data specific analytic workloads. It has real-time query performance for partitioning, parallel processing, and in-memory columnar indexes, which enables real-time complex analytics and artificial intelligence, not just simple time series aggregates. It has Azure IoT integration via built-in interfaces to Azure IoT Hub, MQTT, Postgres via protocol, JDBC, REST, and also a native .NET Core driver. So I'm proud to present before you the industry's first IoT database quadrant. So this quadrant works in the context of IoT, machine data, and digital industry, basically the third generation of databases that we talked about. So when it comes to define the market's most efficient and most scalable database in terms of resource effectiveness, hardware costs, productivity, write and read power, you'll find that CrateDB is at the right spot. CrateDB uniquely combines standard SQL with NoSQL benefits, and its shared nothing architecture gives it an edge in these use cases. Compared to Elastic, which is really close to Crate's efficiency and scalability status, Crate delivers more efficiency. Compared to Cassandra, which shows more scalability, Crate shows far more efficiency. And if you take a look at the position of MongoDB, you'll realize that the way it is positioned there is because it belongs to the second generation of databases that we talked about. It is just like using a butter knife to chop down a tree. So MongoDB doesn't show much efficiency and scalability in an industrial context because it doesn't need to, as it's purpose-built for web scale application, and it's perfect for what it does. Until recently, workloads like these often required a NoSQL solution, like Cassandra, Elasticsearch, or InfluxDB, often in combination with a traditional relational database. But CrateDB makes it possible to handle them in a single system without sacrificing the familiarity and power of SQL. Let's talk a bit about the smart factory use case before getting to our case study. Smart factories have a huge number of sensors for monitoring a large variety of things, such as temperature, pressure, or humidity. Every day, millions and billions of data points are generated by sensors in smart factories, smart cities, and the health industry. This data needs to be ingested in real time. And since the different sensors are produced by different manufacturers, this data tends to be complex and can be in many different forms. This data also has valuable insights about the operation which can be obtained from it by performing analytics on the data in real time. So queries like aggregation and time series analysis, along with machine learning or predictive analytical models, are often applied on this data. The insights that are produced by these analytical operations can be used to take action to improve the efficiency and functioning of these various industries, hence causing significant cost reductions. The differentiating factor as compared to other time series use cases that should be kept in mind is that these real-time queries are under highly concurrent load from stream processing and machine learning and must access gigabytes to hundreds of terabytes of data. Now, to demonstrate the efficiency and scalability of CrayDB, I would like to share with you a story of one of our customers named Alpla. So most of the people in the world use their products at least once a week, be it Coca-Cola, Head and Shoulders, or Dove. Alpla is quite well known in the consumer packaged goods market for its innovative packaging systems, bottles, closures, and injection molded parts. In 2017 alone, Alpla produced over 100 billion consumer good packages. And with over 100,000 tons of recycled plastic, it is also one of the leading packaging companies when it comes to plastic minimizing and minimizing plastic waste and also maximizing plastic reuse, also known as the closed loop plastic economy. We have been working with them from the past 3 years. So this is where real-time information from the production flow has a potential to add value to 180 manufacturing sites in 45 countries. They have sensors for temperature, pressure, blending ratio, and other settings that need to be really precise on every machine. So when these settings are right, high quality products are the result. And when these settings are off, quality suffers and production costs increase. Imagine a factory with 4 production lines, and each of these lines, let's say, have 4 pieces of machinery each. So in a factory flow, they usually have some sort of visual indicator, which shows if everything is working smoothly or not. So in order to discover these issues, multiple people were required to be continuously moving around the factory, checking up on every machine. One of the typical scenarios that can happen is that an employee is currently looking on fixing something on the production line 1. Once they finish that, they go through the other lines to check up on the machines. And that is when they spot an issue on production line 3, machine 4. Upon taking a look at what's up, they realize that there are some parameters that need to be adjusted on the first machine in this production line. And then the person moves again to the first machine to fix the underlying issue. So in factories, the production lines are laid over the whole factory, and distances between machines can be considerable, meaning that this was a slow and labor-intensive operation. Additionally, the latency that was introduced by having to walk around the factory meant that products were often affected by a defect before the error was even spotted by an operator. So this resulted in the loss of valuable machine time and a loss of raw material as defective materials are produced till the problems are fixed. So Alpla's market entry in North America in 2001 was followed by years of tremendous growth. So in 2015, it was already operating 14 manufacturing plants with more than 1,000 employees in the USA. So with this growth came the challenge of hiring and training enough personnel to run the complex manufacturing processes. And because modern manufacturing machines each have a different sort of complex user interface, every plant required specially trained experts for every machine on every single shift. So as a result of rapid growth, database performance degraded. Response time for queries got longer, and any analytics work on the data was taking more and more time. So real-time actionable guidance on the production floor was not possible. CrateIO built their proof of concept on top of CrayDB Cloud and enabled them to drive technological transformations. So the first step was to send data to CrayDB alongside the existing SQL database. So performance of the system improved immediately. So reports and analytics could be generated in seconds instead of minutes. And the system became capable of giving real-time guidance for workers on the production floor. So this allows Alpla to establish a closed loop of continuous production state monitoring and process improvement based on data that is read from these very machines. So when the Crate IoT data platform detects or predicts an unusual change in data, it alerts an expert factory operator in mission control. So the mission control for Alpla is based in Atlanta, and this picture is actually from the mission control in Atlanta. And the mission control looks like this with dashboards for different factories from which we got the raw data. Now the operator alerts somebody at the machine in the factory via a mobile notification system, suggesting either an adjustment or a repair. Now, since employee on the production floor has real-time actionable guidance, while they are working on fixing the first issue, they would get a notification that something is up on production line 3, machine 4, and that that person needs to make adjustments to the first machine of that line to resolve that issue. This way, once they are finished with their current machine, they can head over directly to line 3 and machine 1 to resolve the next issue. And after the issue is resolved, the factory operator logs a note explaining how the issue was resolved. So notes are shared via online manuals across all factories to improve knowledge sharing of best practices. And that is how we close the loop by using this data to take real-time actions on the factory floor. Every plant in Alpla using CrayDB saw improvements in net equipment efficiency, with some having efficiencies above 90%. Every plant also saw a reduction in manual process adjustments by as much as 50%. And reducing the number of manual adjustments stabilizes the process and significantly improves production efficiency. The result was a six-figure saving in 2018. Currently, there are about 2.5 million queries per day, and work hasn't even finished yet. It is estimated to increase 18 times by the end of 2020. And with this, I would like to conclude today's webinar on Success in the Age of Digital X, the Grand Quadrant of IoT scale databases. We talked about the 4 industrial revolutions today: sensors in factories, learned why digitalization projects fail, the CrayDB ecosystem, the quadrant of IoT scale databases, and we finally did a case study on how Alpla made technological transformations with CrayDB, along with sweet six-figure savings in 2018. If you have any other questions or interesting project ideas, feel free to reach out to me on these, or either from my Twitter or the email, and I'd be really happy to collaborate. I look forward to seeing what you do with this. Thank you.
Hi there, Tanai. We've had a couple of questions come through. Would you like me to read them out?
Sure, let's do it.
Okay, so the first question is, how would CrateDB connect to OPC UA factory floor?
All right, so our clients usually connect to OPC UA via Azure IoT Hub, and we have an official connector for the Azure IoT Hub. So you can push data to that from the factory floor and then retrieve with our consumers that we have, and push the data to CrateDB. But it's also possible to use RabbitMQ.
Okay, great, thank you. So the next question, I'm just pulling it up here, is please can you elaborate on the difference, so the pros and the cons, between Kafka, KSQL, and CrateDB?
Oh, sure. So we don't currently have an official white paper on it at the moment, but that is something we are working on. However, having said that, Kafka is intended to be a streaming service, whereas CrayDB is a fully fledged database supporting more NS as SQL. So KSQL is just a SQL wrapper on the streaming data in Kafka and is intended to provide information about currently streaming data. So with CrayDB, you can store data in a hot manner as well as provide a more holistic view of the data.
Great, thank you. And then there's one more here that I can see. So it's regarding the Alpla example that you showed. So how is the data from Alpla handled by CrateDB? And then there's a second part, how much data, how many data points does it have? And what's the data volume like?
Okay, so always happy to talk about the Alpha use case. So essentially, we get raw data from the factories, and these are in many different forms because we are receiving this data from around 950 different sensor data types. So each of them comes in the form of a JSON object, which looks wildly different from each other. And then this is enriched by an enrichment module and then stored into a metrics table. So enrichment module, what it basically does is add some more context to the information and also splits the whole JSON object into different columns while making it strongly typed. Because once the data is coming into a raw table, it's a dynamic type object, and strongly typing it really improves the performance of the queries. And I'm just taking a look at the dashboard here. So the real production data is about 1.5 billion data sets, which amounts to currently about 581.8 gigabytes of data. So data is streamed in real and near real time to enable alerting. But we also store all the data in raw and enriched format in CrayDB in the form of cold storage. So if you include the enriched metrics table along with the raw data, which exists at the cluster, we have somewhere around 3 billion records of data.
Great, thank you. So they were all the questions that we had. So I think we can wrap up.
Sounds good.
I just want to thank everyone for joining then, and please check out our next webinar, which is taking place next week, which is talking about CrateDB Cloud on Azure. Thank you.